In this video, we're going to talk a little bit about determinants. Determinants are really another useful tool for talking about singularity and non-singularity of matrices, and have some additional useful properties as well. So how do we know that a matrix is non-singular? Well, one way we could test is to compute or attempt to compute an inverse, and if it's not possible, then we know it's not non-singular or that it is singular. However, if we do get an inverse, then we know it is non-singular. Similarly, we could try to complete reduced row echelon form on a system involving a matrix equation and figure it out that way. Now remember, so this is really just synonymous to invertible. Well, one way we could kind of formulate a general statement, because of course we could check this on individual examples, but we can start to ask the question, suppose we have a system of the form little ax plus by equals r and cx plus dy equals s. Well, that makes the coefficients a, b, c, and d in this matrix a, b, c, and d. And this is really what we need to figure out whether this guy is invertible. Because if this guy is invertible, then we know we can formulate the ax equals b style equation here, and that we could then proceed to multiply by the inverse. So in particular, what I guess I'm aiming at is that we can write the system this way, and if an inverse exists, then we can multiply both sides by a inverse, and we get identity x equals a inverse b. And so in that case, x equals a inverse b. So yeah, we could obviously carry out the operation, but is there a quick way to tell? Well, let's see for a second. So if we were to find an inverse of the matrix a, b, c, and d, we would proceed as usual if we were to use reduced row echelon form, except now we're going to do it symbolically. So again, what we want to do is we want to eliminate, do some process of elimination here and get this into the identity matrix, and this side is the sort of the one matrix that keeps track of all the operations that we've done so far. And so the first thing I'll do here is I am going to want to cancel out the a, so I'm going to need to multiply row 2 by, let's see here, I'm going to need to multiply it by negative a over c times row 2 and add it to row 1. That might seem less obvious, but if you notice that if you multiply c by negative a over c, you get negative a. And in that case, this leads us to the reduced matrix. Negative a over c times c is negative a, plus a is, oh wait, I take that back. We want to do the opposite. What we want to actually do here is we want to multiply row 1. We want to cancel out row 2 with it. So we'll multiply row 1 by negative c over a and add it to row 2. And what that'll do is, again, what we want to ask is, what do I need to multiply a by? I'll call this k in order to get the opposite of c. And so that would tell me to multiply by negative c over a. And so when I do that, the first row stays the same. And the second row now becomes, well, negative c over a times a is negative c. Negative c plus c is 0. Negative c over a times b is negative cb over a. Excuse me. Negative cb over a. And then what I need to do is go ahead and add that. And, excuse me, so multiply negative b times negative c over a, and you get negative cb over a, and we're going to add that to d, so we have plus d. So this is becoming kind of a messy, hairy process because we are working with symbols, and there's no way to convert this into numerical coefficients. And now what I want to do is figure out what I need to multiply this guy by. Oh, I need to do the same thing here. So negative c over a times 1 is negative c over a. Negative c over a plus 0 is just negative c over a. And so now I need to proceed to figure out what to multiply this guy out to cancel the b. So what I want to know is negative cb over a plus d times what will give me the opposite of b, so that I can figure out what to multiply this row by, add it to this row in order to cancel out the negative b. So I'm going to do a little bit of reduction here. It's pretty algebraically intense. I'll get a common denominator here, so this will be negative cb plus ad all over a times k equals negative b. And now I could solve for k, so divide both sides by this here, or multiply both sides by the reciprocal, so I get negative ab over negative CB plus AD. And so I'm going to multiply this row by it and add it to this row. And so what that's going to leave me with is A0, 1. Now I've got to multiply this guy by this ugly coefficient. And as opposed to going through this whole process, and you can hopefully see how we would proceed to try to cancel things out and get it into the form 1, 0, 0, 1. I'm not going to go ahead and proceed to do this because it is just a very messy, hairy process. But what we do end up with is this. So this is kind of walking through the algebra that we just performed. We got some of this information here, and if we kind of proceed in this way and we keep going and we keep going and we keep going until we get 1, 0, 0, 1 on the left-hand side of our augmented matrix, and then this is what we'll have on the right-hand side. And so thus that would lead us to conclude that A inverse is equal to all of these coefficients D, B, C, A all over AD minus BC. AD minus BC, AD minus BC, AD minus BC. So how do we now know, looking at this symbolically, whether the inverse exists or not? Well, the only way that it won't exist is if you get an issue mathematically. And the only issue that we can have here in calculating this inverse is if the denominator is ever equal to 0. In other words, if AD minus BC equals 0, then A inverse will not exist. So I'm going to come back over here. And here are some properties. So let's get this pointer out here real quick. So if AD minus BC equals 0, AD minus BC equals 0, then A inverse doesn't exist. Right? Again, that's because this was in the denominator of A inverse. If AD minus BC isn't 0, so it could be anything other than 0, well then we don't get a divide by 0 error, and that tells us that A inverse will be calculable. So that would say that it does exist. And so this AD minus BC is what we call the determinant of A. So the determinant of A, written in two ways, you could write it this way, and it determines, if you think about it, whether the matrix is singular or non-singular. So the determinant of A, sometimes people write it this way. They use horizontal lines to say, okay, the determinant of a matrix, determinant of A would be equivalent to writing the vertical bars A, B, C, D, is computed by taking AD minus B times C. And a lot of people see it this way. It's the product of the diagonals here minus the product of the diagonals here. So AD minus BC, or CB. And so this is just restating. Well, this thing is called the determinant. And we wrote up here that if AD minus BC is 0, i.e. if the determinant of A is 0, then A is singular. That means it's not invertible because you'll get 0 in the denominator. If the determinant of A is not equal to 0, then A is non-singular, which means that A has an inverse. And it's as simple as that. So let's actually go through and compute a couple. So let's just say that we have, for example, we can pick any 2 by 2 matrix here. Let's just say that we start off with 3, 4, 2, 1. Okay, so this is A, and the determinant of A would be the cross product, the difference between the diagonal product. So 3 times 1 minus 2 times 4, and that equals 3 minus 8. And in this case, we're not really concerned about the value, but numerically, it's not equal to 0. So that means that matrix A does have an inverse. And how long did it take us to compute that, just to realize that A is invertible and it's worth the time and energy to go through that process? So this is a nice, quick way to check things. What if, on the other hand, determinant of A is 0? How could we kind of intuitively try to understand based on that matrix? Well, here's the matrix 2, 4, 6, 8, and the determinant of A is, again, the difference between the diagonal products, 2 times 8 minus 6 times 4. Let me change this up real quick. Okay, so I actually changed it to 3, 4, 6, and 8, and because I wanted to work out that the determinant is 0. So 3 times 8 minus 6 times 4, again, product of the diagonals, is going to give me 24 minus 24, which is 0, which means, leads me to the conclusion that since the determinant of A is 0, then A is singular. So that must mean likely that that one row is a constant multiple of the other. So if I look at the row 3, 4 and the row 6, 8, the question is one a constant multiple of the other? Well, yeah, absolutely, because if I double the components of the first row, then I get exactly the components of the second row. And so if you were to do reduced row echelon form, what you'd end up with is something like this. The second row would cancel out and leave us with basically either, well, most likely an overdetermined system. So that's how we would check the determinant of a 2 by 2. Well, how about a 3 by 3? Because in that case, it's not quite as simple as trying to multiply across. You would think that it would just be 1 times 5 times 9 minus 7 times 5 times 3, but it's not quite that simple. So what we actually need to do here is we need to come up with some definitions. Now, the way we would come up with a 3 by 3 is much the same way we would come up with the determinant of a 2 by 2, kind of going through that generic process back here of trying to do all this heavy algebra. But the pattern, mathematicians noticed, would look like this. They needed to define a few terms, first of all. So Mij is what we call the minor of A. And this is the matrix that we would form if we were to delete the ith row and jth column of that matrix. So for example, if I wanted to look at M12, that would be the matrix that would be left over if I crossed out the first row and the second column of that matrix. So M12 would be the result 4, 6, 7, 9. That would be the resulting, what we would call the minor. And so the beauty of the minor is that it takes this is kind of the major matrix, and a minor of that matrix would be found by deleting one of the rows and columns. So similarly, M13 would be what we would get if we wiped out the first row and the third column, leaving just this portion here, which would be the matrix 4, 5, 7, and 8. And then M11 would be the result of, let me take out my eraser here real quick. That would be the result of crossing out the first row, first column, and that would leave us with the lower 2 by 2 right there, 5, 6, 8, 9. So we've just basically put together the minors of this 3 by 3 matrix. The next thing we need to define is Aij is going to be called the cofactor of A. And this is sort of a weird thing, but again, this is sort of based on the pattern of things, that Aij is equal to -1 to the power of I plus j times the determinant of Mij. So in this case, let's figure out what those components would be. So we need the minor before we can compute this, because the minor, or the cofactor of A, depends on the corresponding minors of A. So for example, if I were to compute the same minor cofactors for the minors that I have, then the way that would work is first of all, I would compute let's do A11. So A11 would be the first row, first column cofactor, and we're told that that equals -1 to the I plus j power. Well, in this case, I is 1, j is 1, so this is going to be to the 1 plus 1 power, times the determinant of Mij, which in this case would be M11. So the determinant of Mij, or M11, well, let's figure this out. So -1 to the second power is +1, times the determinant of M11, which is the determinant of this guy, would be the product of the diagonal, or the product of the diagonals and then the difference between those. So 5 times 9 minus 8 times 6, which is 45, minus 48, which is -3. A12 would be calculated by taking -1 to the I plus j power, which is 1 plus 2, determinant of M12. Okay, so that's going to be -1 to the third power is -1 times the determinant of M12, which is 4 times 9 minus 7 times 6. And that's going to equal negative 1 times, let's see, 36 minus 42 is negative 6. Negative 1 times negative 6 is positive 6. And finally, I'm going to just show the computation of A13, which is negative 1 to the 1 plus 3 power. That's the sum of the indices of where that component is, times M1, the determinant of M13. Negative 1 to the 4th power is positive 1, times the determinant of M13 is 4 times 8 minus 5 times 7. And that's going to be 4 times 8 is 32 minus 35 is negative 3, so I get negative 3 in this case. All right, well, those are the cofactors, or some of the cofactors. I could obviously come up with a cofactor for A21, A22, A23, etc., but I'm not going to do that because the next component shows me that this is a little bit hard to see. Let me see if I can go ahead and copy this and paste it into a new matrix or a new slide. Try that again. Okay, and so what this now tells us is that in general, the determinant of any A square matrix A, it has to be square because we know that inverses only exist for square matrices. Not all square matrices have inverses, but some do. And this says take the 1, 1 component of the A matrix. Remember, the lowercase is reserved for elements of the A matrix, times the 1, 1 cofactor, plus the first row second column element of A times the A1, 2 cofactor, etc. down the line until basically you get through all of the columns of the first row. So if we back up, we can put these pieces together, and we already know that A11 is negative 3, A12 is 6, A13 is negative 3. So let me write this down. So we know that A11 is equal to negative 3. A12, excuse me, is equal to 6, and A13 is equal to negative 3. Now I just need to get the A11, A12, little a13 components. Now I only go up to the third column, so because it's a 3 by 3 matrix, so in this case my n is 3. And if we remember, A is the matrix, I think 1, 2, 3, 4, 5, 6, 7, 8, 9. So I'll write that down, 1, 2, 3, 4, 5, 6, 7, 8, 9. And so this guy right here is the A11, this guy is the A12, and the A13. And so what I can do now is I'm going to write those down right beside it. So this is more of a really long procedure in general than it is anything conceptually very exciting, but nonetheless it can be done. And so the determinant of A, of this matrix up here, is going to be 1 times negative 3 plus 2 times 6 plus 3 times negative 3, which gives me negative 3 plus 12 plus negative 9. Negative 3 minus 9 is negative 12, which gives me a determinant of 0. And so what that tells me, going back to what we already know, that the same type of rule applies. The reason this ends up being the determinant is because it ends up being what's in the denominator of A inverse if you calculate it symbolically. So this means that A is not invertible. Well, what does it mean if A is not invertible, or A is singular? Well, that means that one of the rows is a constant multiple of a linear combination of the other rows. And we could actually verify this, but we can probably pretty easily observe that if I write this out, that 7, 8, 9, that row, the third row, can be written as 2 copies of the second row, 4, 5, 6, minus 1 copy of the first row, 1, 2, 3. And just to verify this, 2 times 4 is 8, 10, and 12, minus 1, plus negative 1, negative 2, negative 3, and I get 8 minus 1 is 7, 10 minus 2 is 8, and 12 minus 3 is 9, which is exactly the third row. So this determinant just verifies that yeah, you're going to try to do reduced row echelon form, but ultimately you're going to cancel out one of the rows completely, and you're not going to be able to get um, the process through an identity matrix. So, well, why is it singular? Oh, yeah, we just wrote this out. So because 7, 8, 9, for example, could be written as a linear combination of the other two rows, and that's exactly what leads us into that state of having not being able to get the identity matrix through that reduction process. Well, how about a 4 by 4? Well, we're not going to walk through this whole process because, as you can imagine, this gets hideously complicated very quickly. But we would go through the same process. We would set up M11, and M11 would be the minor that we would get if we crossed out the first row in the first column, which would be a 3 by 3 matrix, 6, 7, 8, 10, 11, 12, 14, 15, 16. M12 would be a similar process, except that would be the crossing out the first row second column, and M12 would be, let's see, 5, 9, 13, because we're crossing out the second column instead of the first, but still the first row, 7, 11, 15, and 8, 12, 16. Okay, well, the reason I'm pointing this out, and we can keep on going, M13, M14, all the way up to M14, but now I would need to do each of the cofactors. So A11, recall, is A11, I take that back. A11 is -1 raised to the 1 plus 1 power, and that's all nice and dandy. But now we have to take the determinant of M11. Okay, well, how do you find the determinant of M11? Well, M11 is a 3 by 3, which means that to find the determinant of M11, I have to go through this whole cofactor process again. So what I would have to do now is I would have to compute each of the cofactors of this matrix because it's a 3 by 3 and the determinant isn't as straightforward as we'd want it to be. And so I'd have to create, maybe I'll call this N11, and N11 would be the matrix that I would get if I crossed out the first row, first column of that, and that would be 11, 12, 15, 16. And so now, so this is a nested determinant that I need to find as part of this bigger determinant. It's a mess. It's a big, big nightmare. So the end of the story, without going on any further, is that determinants of matrices larger than 3 by 3 quickly explode with computations. And we could do this very easily in our calculator. Before we do that in our calculator real quickly, here are some properties of determinants that we'll really want to be familiar with that'll become useful. So let's look at 3 elementary matrices, type 1, type 2, and type 3. Then we can conclude that the determinant of an elementary matrix times our square A matrix is going to simply be the negative of the determinant of A. So what does that tell me? Well, type 1 matrix is one in which I basically multiply or interchange 2 rows, right? So if I interchange 2 rows, like for example 1, 2, 3, 4, that matrix right there, and I look at the determinant of this guy, the determinant of the matrix right there is going to be 1 times 4 minus 3 times 2, which gives me 4 minus 6, which is -2. And if I switch the rows, the determinant of 3, 4, 1, 2 would be 3 times 2 minus 1 times 4. In this case, 3 times 2 is 6 minus 4 is +2. So we can see that if you switch 2 rows, that's going to simply invert, not invert, but take the opposite sign of the determinant of the matrix without switching the rows. In this sort of same fashion, we could demonstrate that if you scale a row, so let's say alpha equals 2, and I scale the first row by 2, so I would get 2, 4, 3, 4. So all I've done is I've scaled the first row, and the determinant of that is going to be 2 times 4 minus 3 times 4. 2 times 4 is 8 minus 3 times 4 is -12, which is going to give me a determinant of -4. And again, look at the relationship between the original determinant and the scaled matrix determinant. One is just twice the other. In other words, if I multiply a row by alpha, the determinant is scaled by a factor of alpha. Pretty nice, right? Pretty simple. And in a similar fashion, we could prove that if you add a multiple of one row to another row, the determinant of that does not change. So, for example, if I took let's say I took 2 times row 1 and added it to row 2. Okay, now not because there's really a good reason to do that, but just to demonstrate, 2 times 1 is 2 plus 3 is 5. 2 times 2 is 4 plus 4 is 8. And to calculate the determinant of that, I would again do 1 times 8 minus 5 times 2. 8 minus 10 is negative 2, which gives me the same determinant as if I were not to multiply a row by a constant and add it to another. So this is kind of this is not really proof. Again, we can't prove by example, but this just demonstrates that it is true and hopefully gives some intuition that, that whenever you do scale something, that you're going to be scaling the determinant, since you're scaling 2 of the values involved by that same factor, right? This guy and this guy both get increased by the same factor. And finally, one last one. If A and B are both square matrices, then guess what the determinant of the product is? The determinant of the product of A and B is simply the determinant of A times the determinant of B, which is, again, very convenient, because if I know the determinant of each one individually, then I can simply find that and multiply those determinants together. Now, not all things work this way. In general, you can't just take a function and take the function of A times the function of B, but with the determinant operator, you can. As one final note, we'll just show how to do this in the calculator real quick. Okay, so here I just have a 4x4 entered in, just kind of a random one that I had left over from another example. So I have this 4x4 matrix in here. Again, this would be awful to try to find the determinant of manually. So what I'm going to do now is exit back to my home screen, and what I want to pull up is the determinant function, which will go to second x inverse, and then what we want to do is go into the math menu, and the first option is the det, or the determinant, and now I can go pull in matrix A, and the determinant of A is 97. So that number itself doesn't really mean much to us. It doesn't really tell us anything except that it's not 0. And since it's not 0, that means that A is invertible. And of course, we could try to invert A and see if it's possible, and it should be, because of the determinant being 97 and not 0. And so there's the ugly looking determinant of that matrix, and your calculator can obviously find that very quickly. So that's really all there is to determinants for now. We'll use them later, and we'll use their properties. It's not something that's super duper critical to every study, but determinants are a valuable tool to have, especially when we're trying to make an argument about whether some technique is going to be possible. And so that's it. Hope this has been helpful, and let me know if you have any questions.